guys, welcome back to my channel, and today what we will be doing is we will discuss Google's page rank algorithm. Page rank algorithm. Algorithm. So what this algorithm does is whenever you search anything on Google, let us open Google and see it for once. Whenever I am searching anything over here, say we search Mysore city. So how is Google ranking which page to show first? There are so many results related to Mysore city. Then how it is deciding which page to display first, which web page to display second. So that is all about Google's page rank algorithm. Okay. So, and it is using a mathematical concept called Markov chains. Okay. What Markov chains are? Well, any Markov chain in this, the the next state depends on what is our current state. Depends on the current state. The current state of the system. Okay, we will understand this as we see the page rank algorithm. Okay, so these are interdependent probabilities, they are not independent events. One, the next state, it depends on what is the current state you are in. Okay, let us see. So in Google's page rank algorithm, what happens is there is a web crawler. Okay, before understanding web crawler, let us see there are, let us say in our web internet there are only four web pages for simplicity. Okay, there are four web pages: A, B, C, D. And in any web page you will see, if I click Wikipedia for example, if you click on this, you will link to another page. So these links in the graph, in the model, we will represent as directed edges. Okay, so when you click on web page A, some link, you can reach web page B. You can from B you can reach A, from A you can reach D, and from D you can reach again B. From from B you can reach D, and from D you can reach C, from C you can reach D, from A you can reach C. So this is your web graph. This is your web graph on the internet. Okay. So what will happen? There would be a web crawler. What this web crawler does is, starting from any of the web pages randomly, for example, it starts from web page A. Now whatever links from whatever hyperlinks web page A is connected to other web pages, randomly it will choose one of the web pages and go to that web page. And as soon as the web crawler moves to another page, it increases the rank of the pages as it visits. So the web pages that randomly gets visited the most, its rank would start to increase. Okay, so how do we model this is, then this web crawler, this type of walk where the randomly the crawler or the robot or the program is selecting one of the neighbors of this web page and moves to that web page randomly, is this is known as a random walk. This is a random walk because it is walking on these web pages randomly, right? So so the rank of any web page, initially, for example, in the beginning, before visiting any of the web pages, the rank of our web pages A, B, C, D, where I will write it as A naught, B naught, C naught, D naught. These are the ranks initially. As we have 4 web pages, so we will give rank 1 to each. 1 by 4, 1 by 4, 1 by 4, 1 by 4. So this is our initial rank R naught. Okay. Now what we will do is, in the next page we will write the linking matrix L. What does this linking matrix mean? This matrix will show from A. From A, what is the probability that this crawler will move to B, C, D or A itself? I know how many outgoing edges this A web page has. It has an outgoing edge to B. It has an outgoing edge to C. It has an outgoing edge to D. It has 3 outgoing edges, right? So, we will write this matrix as A, B, C, D. Okay. A, B, C, D. Okay. The columns of this matrix would represent the columns of this matrix would represent the outgoing edges. Okay. Initially, the rank of A was A naught, the rank of B was B naught, C naught, and D naught. Okay. So from A naught, what is the probability the crawler will move to B naught, to D naught, and to C naught? I know it is having 3 outgoing edges, so it has 1/3 the probability. I know from A, next to going to A, from A to A, the probability is 0, to B is 1/3, to C is 1/3, and to D is also 1/3. Okay. What about B? Number of outgoing edges from B, we will write it with another color, green maybe. So from B naught we have 1 outgoing edge and 2 outgoing edge. So it will move to either A or D. Okay. So next rank. Okay. Next rank B, it cannot move to A. It is moving to A, right? It is moving to A with 1/2 probability. Sorry. We will erase this. It is moving to A with half the probability. It cannot move to B. What about C? It is moving to C with 0 probability. And D, again half probability. Okay. Then what about C? C has only 1 outgoing edge to D. Right? Whatever rank C had, it will give entirely to D. Right? So C cannot move. C has no outgoing edge with any other, only with D. So it is having 1. What about D? How many outgoing edges D has? D has 2 outgoing edges, right? To B and C. So to B and C. Okay. So this matrix is representing, if you give as input to this matrix the initial ranks A naught, B naught, C naught, D naught, this matrix, when you multiply A naught with the first column, B naught with second column, C naught with third column, and D naught with the fourth column, it will give you the new ranks as outcome. So A1 will be equal to half of B naught. What about B1? The new rank of B after this calculation would be 1/3 of A naught, 1/3 of A naught plus half of D naught. Then 1/3, the C's new rank would be 1/3 the old rank of A naught and half half the rank of T naught, old rank of T naught, right? And what about D naught? The rank of D naught is calculated using 1/3 the rank of A naught plus half the rank of B naught plus C naught, complete rank of C naught. So from here we know that the rows, they are representing how the original rank, the old ranks of the web pages, how much it will be contributing to the new rank of this web page, right? And the columns are representing the number of outgoing edges from that, how that old rank is being distributed among new ranks, right? Yeah. So for any web page, the columns are representing how the old rank A naught is being distributed to the new ranks, and the rows are representing every new state, how it is being calculated, new rank, how it is being calculated from the old ranks, okay, or the incoming edges, okay. So the new rank for any web page is decided by three factors, okay. So first factor is what was the old, is my web page, the neighbor of it from which we are, this web crawler is visiting this new web page, is it, what is the rank of that old web page, okay. So what's the rank of the old web page uh, through which web crawler has reached the new web page, through which web crawler reached new web page. So if your old web page, suppose you are visiting B, you can visit B from D. So if your D is a very highly ranked page, then definitely your rank of B would increase, right? So if you are connected to a very popular page, then the neighbors of that page would also be of higher rank. Then second, are you linked to A? Suppose if we are finding the new rank of A. So other pages have what's their rank, and are they connected to this A or not? That determines the rank of new rank of A. Do you link to A? Do you link to A? And third important factor is how many outgoing links you have. If your page D naught suppose is very popular, it has many incoming edges, okay, and its old rank is also high, and it is also linking to web page B, for example, okay. But if it has many outgoing links, then it will choose randomly B naught to go to next. That depends on how many outgoing links it has, okay. So outgoing links of a web page is also an important factor to calculate new rank, to calculate new rank of connected web pages, okay. Yeah, so you can find, if you keep on finding, if you multiply, suppose we will write the ranks, the old ranks as R, okay. So you can find the new ranks iteratively. So new rank R1 will be equal to L times R0, R2 will be L square, 2 times you multiply to R0, or you can write it as L times R1. L times R1 will be your R2, that is also same as L times R0, that is L square times R0. Similarly, R nth, after n time intervals, what would be your new rank would be equal to L times R power n minus 1. That is same as uh, L power n times R0, right? And a matrix, the power of the matrix can be calculated using eigenvalues, right? You can break this L matrix, linking matrix, as the S inverse or L inverse. L inverse lambda ki power n and L times R0, right? And that is equal to Rn. And after infinite, when n tends to infinity, then what will happen? All the eigenvalues, they will become very small. Only the eigenvalue 1 will be relevant at steady state. So at the infinite term or the steady term that will not change any further will be the ranks that will become stable. After infinite time, what will happen? Your, even if you multiply with L, the next term would not change. It will converge to a steady rank value. And that will be equal to your L lambda power infinity L inverse R0, and all the other eigenvalues will be very small. Only eigenvalue 1 will be relevant over here. So it will, R infinity will become L, only one eigenvalue 1 power infinity would be relevant, L inverse R power 0. Okay, so that you can, without finding the eigenvalues also you can find that. So that will be become equal to R will be equal to L R. And if you write, if your number of states in R is very less, then you can write it as A0, sorry, A, B, C, D would be equal to, at infinity, the A infinity, B infinity, C infinity, D infinity, the ranks would be equal to the matrix L that we wrote over here, that we wrote 0, 1 by 3, 1 by 3, 1 by 3, 1 by 2, 0, 0, 1 by 2, 0, 0, 0, 1, yeah, and 0, half, half, 0. A infinity, B infinity, C infinity, D infinity. If you solve, you will get 4 equations and you will get the values of A infinity, B infinity, C infinity and D infinity. Okay. And use one more equation, that A infinity, because they are all probabilities, right? So A infinity plus B infinity plus C infinity plus D infinity will be equal to 1. You solve these 4 equations and you will get the answer for steady state value of the ranks of the web pages. Or you can find using eigenvalue decomposition as S lambda R0 into L inverse lambda power n lambda also. Then lambda into lambda inverse, you will get a constant R0. Okay. All right. Okay, so that's it for this video. Hope you uh, hope you like this video. Okay, one more important thing, at steady state value, the eigenvector for lambda is equals to 1 only matters. Okay, only for lambda eigenvalue 1, the corresponding eigenvector will be relevant. Other eigenvalues at infinite term, they will become very, very, very small. So they don't contribute anymore. Okay. So hope you like this video. Please share it with your friends and subscribe to my channel. If you want to explore how to find the value of S inverse lambda ki power n s, the powers of the matrix, the powers of the matrix L, then you can check out the I tab we have discussed in detail over there. And till then, bye bye and take care.